All right, in case 2, we're in quadrant 2. In quadrant 2, the tangent's negative, which means that the absolute value of tangent is the opposite of tangent. And so as we mentioned, we end up getting the exact opposite integral we had before. And so we can go through the exact same process. And what's going to be different? Well, this would be negative natural log absolute value secant theta plus tangent theta plus c. But we know that there's another formula for integral secant. One of them is the natural log absolute value secant theta plus tangent theta plus c. And the other one is negative natural log absolute value secant theta minus tangent theta plus c. And since we're getting that negative anyway, we might as well use the other formula. So this is going to be negative natural log absolute value secant theta minus tangent theta plus c, which gives us this. So now look what happens. If I go back and look at the substitution, x is 5 secant theta. I would go through the same process to determine what the tangent of theta is, and I would get back to plus or minus the square root of x squared minus 25 over 5. But since I'm in quadrant 2 now, I would pick the negative square root. And so look what happens. The negative I had out front, I've taken care of that using the alternate formula for this integral. And now the negative that I have in here, when I substitute that back in, is going to cancel out that negative there. And so this gives me, in the land of x's, the natural log absolute value, secant of theta, which is x over 5, minus a negative square root, that's plus this guy, plus c. And I can do the same trick I did before, get these, since they have the same denominator, use a log property, and take the natural log of 5 into that constant. So in quadrant 1 and in quadrant 2, I'm getting the same antiderivative. And so that means that our final answer can be combined into just one answer, the natural log of the absolute value, x plus the square root, x squared minus 25 plus c. So in this case, the two cases for the secant combined into one case. It doesn't always happen that way. And it wasn't obvious it was going to happen unless we do some identities. That'll do it for part A. All right, looking at part B, the only difference between part A and part B is the square root's not there. So what's that going to do? Well, once again, this is awful close to the inverse hyperbolic, or excuse me, to the arctangent form. Okay, but for arctangent, I need x squared plus 25. Okay, now, depending on how many of these formulas you memorize, you may look at this as a inverse hyperbolic tangent or something like that. But for our purposes, we're going to handle this not using a secant substitution, but using partial fraction decomposition. All right, so when do I use a partial fraction decomposition? Well, if the denominator is easily factorable, which this one is, you can factor this as the difference of squares. I have two distinct linear factors. So I know this is going to break down into some constant a over the factor x minus 5 plus some constant b over the factor of x plus 5. And to determine the a and b, I'm going to multiply through both sides by this denominator. So if I multiply the left-hand side by this denominator, I'm left with a 1. When I multiply this side, I'm going to have a times. The x minus 5's will cancel. I'll be left with an x plus 5 plus b times. The x plus 5's cancel. I'll be left with an x minus 5. Now this equation has to hold for all x's, and so I look to see if there's some convenient choices of x I can pick to zero out, help me determine these constants better. And if I look, x equals -5 looks good, because if I plug in x equals -5, that's going to zero out this first factor. It's going to give me 1 equals -10b, so b is -1/10. I also look, and x equals +5 is a good one to plug in, because that'll make the second term zero out. So I get a is +1/10. So that means I can integrate. To integrate this guy, I'm going to integrate a over x minus 5. So I've got 1/10 over x minus 5 plus b, -1/10 over x plus 5 dx. So this is 1/10, the integral 1 over x minus 5 dx minus 1/10 integral 1 over x plus 5 dx. So this is equal to 1/10 natural log absolute value x minus 5 minus 1/10 natural log absolute value x plus 5 plus c. And if you wanted to, you could use log properties to get our final answer. The integral of 1 over x squared minus 25 dx is 1/10 natural log absolute value x minus 5 over x plus 5 plus c. So that'll do it for part B. Okay, in part A, number 2 here, we've got 1 over x squared plus 25 dx. And we want to integrate that. And this actually is one of our basic integration formulas. We know that if a greater than 0 is a constant, the integral of 1 over a squared plus u squared du is 1 over a times the arctangent of u over a plus c. Alright, so I look at this integral, and what do I notice? The variable u in this case is x. So I don't need to do any substitution. It's x squared dx. And the constant here is 25. So 25, that's the a squared. So that means I can take a to be 5. So I apply the formula. It's 1 over a, 1/5, arctangent u over a, x over 5, plus c. And that's all there is to part A. Okay, in part B, the integral is hauntingly similar to part A, except in part A I didn't have an x up top, and now I do. So what form does this fit now? Well, if I look at the denominator, the derivative of the denominator is more or less the numerator. So I can let u be the x squared plus 25. du is 2x dx, which I more or less have upstairs. So I'll do the usual maneuver. I'll put a half out front, integral 1 over x squared plus 25, and have a 2x dx. And so my denominator is what I'm calling u. And now this is my du. So I have a 1/2 integral 1 over u du, which is 1/2 the natural log of the absolute value of u plus c. So this is a log form. Now, in the land of x's, this is 1/2 natural log absolute value x squared plus 25 plus c. Now, do I really need these absolute values? Well, no. Regardless of what x is, x squared plus 25 is going to be a positive number, and so I get 1/2 natural log of x squared plus 25 plus c. So that'll do it for part B.